Hello class. In this section we're going to be looking at other strategies for integration, and specifically we're only going to look at use of the table of integrals to solve integration problems. And so what I've done here is in this particular folder I've actually put a link to the table of integrals that's in the appendix of this textbook. And I just kind of want to give a walking tour of these integrals. So the first part of the table is basic integrals. These are all integrals. There's the power rule, there's 1 over u, which is the natural log of u, etc. These are all integrals that were introduced in Calc 1. Okay, and most of them are just direct results that can be proven, or direct results from knowing the derivative of a function and knowing that the antiderivative simply goes backwards. Okay. Some of these in Calc 1 took some work to derive, but in a traditional Calc 1 sequence, you essentially derive all of these 17 integrations. Okay, notice that some of these are just the result of, what's the derivative of the inverse sine, and then knowing that you get the antiderivative of, this particular integrand. So in all of these, in 1 through 17, whether you're familiar with them or not, were actually introduced and or proved in Calc 1. Okay, so that's the basic integrals. Moving down through here, we've got trigonometric integrals. And notice they look at different powers of the traditional trig functions. And these we all handled in a previous section in Chapter 3 with power reducing formulas for different powers of, sine, cosine, tangent, cotangent, etc. And those really come from connecting trigonometric identities from pre-calculus to integrating trig functions. Okay, so that's from a previous section, and the power reducing formulas. Same thing here. And what they did here is they nicely came up with a formula for some arbitrary power n on sine, cosine, tangent, cotangent. So that's really nice. Otherwise, this is a lot of work if you have to do more than one iteration of power reducing for these single trig functions. Okay, and we move on to products of trig functions, and these we derived, well, we didn't derive, but we used the identities in product to sum to products in the trig identities from pre-calculus, and that was also covered in a previous section of this course. Okay, so these are nice and handy because this is for arbitrary angles here. All right, and here we've got some more trig integrands with the actual variable here. This would be handled with integration by parts, which we also learned in a previous section of this course. Okay. And here they do it for the general case, u to the n sine u, u to the n cosine u. Okay. And here's another thing that we looked at in Chapter 3 earlier, but they do it for general case here. Okay. All right, for exponential functions and logarithmic integrals, these are going to be either falling from integration by parts or clever substitutions. And so a lot of these really do fall from integration by parts. This one we actually derived in Calc 1. Okay. So most of these with exponential and log functions inside of the integrand, potentially combined with the sine and cosines, really clever substitutions and integration by parts will do most of these. Hyperbolic integrals, we just looked at this in Chapter 2. And so although these things are new, they follow similar type of patterns for the traditional trig integrals. Okay, so this is something we just looked at, the hyperbolic trig functions. Okay. Inverse trig integrals, these were actually looked at in Calc 1. All right, but now we get to a little bit more sophistication because we can combine some of the basic integrals from inverse trig functions with integration by parts, and we come up with a few more difficult or complex integrals in our table. Here we're looking at integrals involving a squared plus u squared, and we had a section prior where we had radicals, a squared plus u squared. And so here they're just looking at forms with a squared plus u squared. Okay, and some of these we actually looked at in a previous section. Okay. And again, some of these are going to result from doing trig substitutions combined with u substitutions combined with integration by parts. All right. Notice I've got a u squared minus a squared. We looked at these again in a previous section, albeit they had a radical, but we looked at these forms as well. And again, integration by parts, trig substitution, clever u substitutions, we'll get all of these. So these integrals in this table aren't something that you couldn't do. You could do these, but it might take some or quite a bit of underlying work. And notice here I've got a squared minus u squared. We also looked at this form, albeit underneath a radical when we did trig substitutions. Okay, so this is a little bit more general, but a lot of these actually have radicals in them. So many of these we actually looked at in homework in previous section. All right. So here, though, some of the last ones here, these are quadratic in form. If you notice 2au minus u squared, I'm looking at something that's almost a quadratic. Well, it is a quadratic in u because I've got a power of 2. And so what they would do here is do a completing the square type of idea combined with some clever substitutions and perhaps some trig substitutions. But these here could be done also with the knowledge that we have. But again, they're posted here in this table. Here I've got integrals involving some linear form, a plus bu. Here I've got a plus bu here, I've got a plus bu here. And we actually just looked at partial fraction decomposition, so we could actually handle these as well using partial fraction decomposition. And notice when we did partial fraction decomposition, we had a lot of natural log components showing up in the final answer. And if you notice, a lot of these have these natural log features, right? So what they are doing to get these are essentially partial fraction decomposition, where they have a constant over this linear form. So again, these we could do as well, but they've posted this in the integral table in the appendix. Okay, so here they're combining a little bit more complex features here. Again, these could also be done with clever substitutions, integration by parts, etc. And so that's kind of a brief rundown of the integral table. Okay, so let's go back to, let's just look at a specific example here. And all right, so using a formula from the table that I just went over, evaluate this integral here. So in the table, the integral of the square root of a squared minus u squared over u squared du has this form. Right, it's got the square root of a squared minus u squared over u with a negative sign minus the inverse sign of u over a plus c. So if we look, we're going to have to do a little bit of work here, because if you look at this form, it doesn't seem to be at face value the same thing here. Clearly a is 4, right? 4 squared 16. If I view e to the x squared, that's going to be u squared. But you might be thinking, oh, well, shoot, there's a u squared here, but I don't have an e to the 2x down here, or e to the x quantity squared. So what's going on here? Well, first you need to do an intermediate step. I would pick a u substitution of just e to the x. So if u is e to the x, this is u squared, this would be u. But remember, when you do a u substitution, you need to differentiate. So if u is e to the x, then du would be e to the x dx. So dx, well, I don't have an e to the x dx. Well, I could put an e to the x there and then divide by e to the x. So I'll force the issue by putting an e to the x here in the numerator and an e to the x in the denominator. So then when I do the u substitution, this becomes minus u squared. Because I multiplied the numerator and the denominator by e to the x, this denominator will be u squared. and the e to the x dx will be my du. All right, let's go ahead and see how the textbook formulates this. So notice here's the original integrand. They multiply the numerator and the denominator by e to the x. With their u substitution of e to the x, this is u squared, this is u squared, and then e to the x dx is simply my du. So we have the exact same form that we can use in the integration table. And so we just write out the formula, but then remember, oh yeah, u is e to the x. So we substitute e to the x squared there. This would be e to the x. Our a value is 4. So 4 squared is 16. This is the inverse sign of e to the x over 4 plus c. And so there we have the final answer. So when you use the integration table, sometimes you're going to have to do some massaging or some algebra or a clever substitution to get it to a form where you can use the integration table. In all cases, when you do use an integration table, make sure you go back and back substitute, right? Our answer isn't this. We have to go back and replace the u with our substitution and our a with 4. So that's our first nice example of using an integration table. I'll do one more example in the following video.